In a comment to an earlier video, someone asked about comparing the FFT operations in some oscilloscopes, specifically the Siglent and the Rigol that I've been comparing. But I realized that to do that, they also suggested that I might want to include the analog discovery. And that presents some interesting challenges as well as some interesting opportunities. So I would like to go down that route, but to do it, I really feel like I need to kind of start back at ground zero, because my comparisons of oscilloscopes have assumed that the audience is electrical engineers, electrical engineering students, undergraduate, graduate, and so on. Well, anyway, to make a long story a little shorter, I'd like to start back with the basics of frequency analysis or fast Fourier transforms. And to do so, I'm going to use the Tektronix oscilloscope. One reason is that Alan, W2AEW, has done a couple of excellent videos on using the FFT functions on oscilloscopes, and one of the scopes he uses is the 100 megahertz version of this scope. This is the 200 megahertz Tektronix, but it's virtually identical to the scope that Alan uses. So I suggest you might want to watch his videos as well as an introduction. Then I'm going to expand on that to kind of go over the basics of frequency analysis, both on oscilloscopes as well as on spectrum analyzers. And then in another section, another entire video, I will go and look at spectrum analyzers in higher frequency domain. And you may notice the frequency on the scope here is 500 kilohertz, and it's a sine wave. Now what I'm going to do, increase the number of cycles on the screen, and we'll talk about that later when we talk about frequency resolution and things of that sort. And I'm going to go to there, and then I'm going to enable the FFT function of that sine wave. By the way, you may notice that we're using DC coupling on this channel. And so there is the FFT function. And don't worry if this doesn't make a lot of sense to you at this time. What I'm trying to show is the things you need to know to be able to work with these systems. And so if some of this seems like black magic, it's going to become much clearer as we move along. But this is the fundamental frequency. That's the 500 kilohertz. And one way you can tell that is if you look up here at position, I'm going to move the position of that peak over to the center, and you see it's 500 kilohertz. Now, what I want to talk about, though, is this spike over here. And that is the folding at the DC level. Don't worry if you don't understand what that means. It's an artifact of doing fast Fourier transforms. The reason that it's important isn't specifically that. It shows up, it fools a lot of people, and they think there's a frequency there. That's not. It's a mathematical artifact. But now look over here at this peak right here, and you'll notice I have a cursor set on that to read the level of that signal. Now what I'm going to do is go back for just a second to the input channel, and I'm going to change the coupling from DC to AC. And then I'm going to go back here to the FFT, and you may notice that that cursor, which used to be at the peak, at the top of this peak, is now significantly above it. That's because that peak is a lot smaller. By going to AC coupling, we have eliminated a large part of the DC component or the DC offset, which is a real problem for FFT analyzers. Once again, if you don't understand this, that's fine. But what I want to emphasize is there's a lot of little nuances to working with this that if you really want to understand what's going on, you need to understand those nuances. So what I'm going to do is to try to give you a bit of a grounding in the whole FFT and frequency analysis. If you already understand fast Fourier transforms and frequency analysis, and you just are interested in the comparison between spectrum analyzers, which I will do later, you might want to skip this entire introductory video and go on to part B. But if you would like either a review or if you've never been through a lot of this, I suggest first you watch Alan's videos. They're very good, W2AEW on YouTube. And then you follow me through part A of this video, and at that point you'll have a lot of understanding of what you're actually doing here. And then we'll move on and we'll do some higher frequency experiments using some spectrum analyzers that go up into the gigahertz range. So before we get deeply into some of the examples, let's make sure we're clear about what it is we want to measure. In an oscilloscope, normally what we are measuring is voltage and time. I know that a lot of oscilloscopes have a frequency measurement, but as most of you already know, all that really is they're measuring the time of a cycle. So for example, a sine wave, and then they are inverting that to get the frequency. That is, 1 over the period equals the frequency. You notice that, for example, when you look at a square wave. Now a square wave, as we'll find out later, has a number of frequencies in it. But what an oscilloscope will display is only 1 over the period. In other words, the fundamental frequency. A spectrum analyzer, on the other hand, is much more related to measuring power. Sometimes it's called the power spectrum or the power spectral density, but nonetheless it's the power and the frequency. So let's review what power is. Power is the voltage times the current. If we use Ohm's law to express the current as E over R, then the power is E squared over R. If you keep this in mind when using a spectrum analyzer, you'll realize why R is important. In an oscilloscope, R is not that important. In other words, you can measure the voltage across any resistor and it doesn't really matter. But when you're measuring power, you have to know what resistance you are measuring. Normally, spectrum analyzers, this will be 50 ohms. The power is normally expressed in terms of a ratio. That is P1 to P2, where P2 is a reference. It can be in watts, in milliwatts, in volts, in microvolts, or a number of other measures. Normally, in a spectrum analyzer, it's in milliwatts. And, as we'll see in a minute, a dB milliwatt, or dBm, is the common reference for a power ratio in a spectrum analyzer. Let's review briefly what logarithms are all about. They're just exponents. If you have a number and you take its logarithm with respect to a base b, and that's equal to m, that's the same as saying that the base b raised to the power m is equal to x. Here's an example. Log to the base 10 of 6 is 0.778. 10 to the 0.778 equals 6. Now, if you don't believe that, let's take a look at the calculator. So we'll enter 6, and we'll take the log of 6, which is 0.778. Then we will raise 0.778, 10 to the 0.778, which is, and we get 6 back again. That is a transform. In other words, logarithms transform numbers into exponents, and raising a number to an exponent transforms it back to a number. One of the interesting properties of using logarithms is that when you're multiplying two numbers, if you're using logarithms, you add the logs, that is, the antilog of the log of x plus the log of y is just equal to z. Now that may seem like a very long way to go about things. Let's give an example, and then we'll see later why that's very important in spectrum analyzers and why it's much more convenient to use logarithms. So 2 times 3, which is 6, is the same as the log of 2 plus the log of 3, which is 0.477, to give us 0.777. Actually, it should be 778 if you include the 0.301, which is the log of 6. In other words, the antilog of 0.777, or 10 to the 0.777, is 6. So, power in decibels uses a logarithmic formula. It just multiplies the logarithm by 10. So if we have a power 1 and a power 2, we take the ratio of power 1 to power 2, then we take the log to the base 10, multiply by 10. Here's an example. If power 1 is 6 and power 2 is 3, in other words, the reference power is half of the measure power, then the power in dB is 10 times the log to the base 10 of 6 divided by 3. That's this ratio. Or it's the same as 10 times the log to the base 10 of 2, 6 divided by 3 is 2, which is 10 times 0.301. The log to the base 10 of 2 is 0.301. Remember, we saw that up here. Log to the base 2 is 0.301, or log of 2. So it's 10 times 0.301, or 3 dB. Now that's a very common measure of power because it's a power ratio of 2. After you've worked with a spectrum analyzer for a while, you learn a few of these power ratios. You sort of memorize them. A power ratio of 2 to 1 is 3 dB. So now let's look at how some of these things are used in a spectrum analyzer. This is a printout from an Anritsu spectrum analyzer. Down in the left-hand corner is the center frequency, CNF. In this case, it's 208 megahertz. Just to the right of that is the span frequency of 500 megahertz, the resolution bandwidth of 300 kilohertz, and the video bandwidth of 100 kilohertz. Now we'll talk about all of these things as we look at the various oscilloscopes, their FFTs, spectrum analyzers, and so on. So you don't need to understand what these are, but notice that all of these are expressed either in megahertz or kilohertz. These are all frequencies, if you will, or spans. At the top is the reference level, which in this case is 0 dBm. That's a decibel to a milliwatt. The attenuator, or the scale factor of the screen, is 10 dB. We just talked about decibels. In other words, each of these sections is 10 decibel. So this is 10, this would be 20 from here, this would be 30 down, 40 down, and so on. So each of these peaks you measure in decibels. The attenuator, which is a normal function in most spectrum analyzers, is set to 20 dB. So that's important because if you measure a signal at, say, in this case, it looks like it's about 16 or 17 dB down. Well, you have to add back the 20 dB that you're attenuating the input. The ST is sweep time. That's the length of time it takes for the instrument to sweep from the left to the right and be ready to sweep again. And the detector type is peak. Once again, we'll talk about all of these, but it's important to realize that the top line is basically has to do with power, which we just talked about is measured in normally decibels. And the bottom line is the frequency. That is, across the y-axis is various frequencies. The center frequency, the span, that is how wide across the spectrum is being displayed, and so on. This is a description or a graphic that illustrates on an oscilloscope in the time domain, normally displaying amplitude with respect to time. If you think of the frequencies that make up that square wave, that's what's represented here. There's a fundamental frequency, in this case a third harmonic. You notice the second harmonic is missing. Third harmonic, fifth harmonic, seventh harmonic, etc. A square wave is made up of odd harmonics. And over here you see in the frequency domain what those harmonics look like. In other words, if you were looking at these signals, these harmonic signals, end on with respect to frequency, that is frequency back this way, this is what you would see. The height of the peak is the power, and the distance to the right is the frequency. A typical spectrum analyzer will work somewhat like this. Now understand, this is not quite what is going on with an FFT in an oscilloscope. We'll talk about that in a minute. An FFT in an oscilloscope is actually a mathematical operation. In other words, it doesn't normally have mixers and things of that sort. Instead, it simply takes the signal in and then does a mathematical transformation on it. But this is a typical spectrum analyzer with the RF input on the left. Normally there are a set of attenuators that allow you to adjust the amplitude of the signal so that it both will display within the range of the unit and also is convenient for whatever it is you're measuring. There is a one or more tunable local oscillators that mix with the signal coming in. Then there is normally an intermediate frequency, that is, it's a superheterodyne, and that is filtered. There is usually also what's called a resolution bandwidth filter. Just think about that as like the IF frequency or the IF filter. It decides how much of this mixed signal, how wide a bandwidth is allowed through to the detection and display unit. Now, to give you an example of resolution bandwidth, here you see two different resolution bandwidths. This is a narrow resolution bandwidth, and this is one that is wide. Same signal under test. With the narrow resolution bandwidth, you pick out the individual peaks, because this is basically sweeping across the signal under test. When it's centered over this one, you see this peak. When it's centered over that one, you see this peak. If the resolution bandwidth is pretty wide, you won't see individual peaks. Instead, the resolution bandwidth, when centered over these, will look like this, and you'll see what is shown in red here. Now, there often is a second filter in spectrum analyzers called a video bandwidth filter, and it is normally just a low-pass filter. The purpose, this part is exactly the same up to the detector, but between the detector and the display, you can insert a low-pass filter that removes high-frequency noise from the signal. Let's look at how that might affect the display. Here you see a relatively narrow video bandwidth filter. Here is a relatively wide one. Once again, roughly the same signal. The result is, and I realize this may be a little bit hard to see here in this light, is that with the narrow video bandwidth filter, there is less noise than you see with the wide filter, video bandwidth filter. Now, there still are occasions where you want to use a wide filter, particularly where you're looking for very narrow transients, because one of the problems with a narrow video bandwidth filter is it will tend to clip or sometimes even completely obscure narrow spikes, narrow signals that have the appearance of noise but exist up in this upper region of the video bandwidth. And of course they'll get clipped by this. So these are some technical aspects of how a spectrum analyzer goes about separating the signals that you want to look at and displaying them on a display. Now we've hooked up the analog discovery. So let's talk about a little of what we have here. At the top is the waveform itself. It's a square wave in this case. If we go to a sine wave, you see what it looks like there. I have this on channel 2, so it's in blue. It shows up a little better than channel 1, which is in yellow. And then down at the bottom there, you see on the far left, this is the FFT using the analog discovery, and you notice that there is a single peak on the left and then just nothing but noise all the way across the rest of the frequency spectrum. So we'll zip back out here a little bit, and then I'll go to a square wave, and you notice what happens to the spectrum. Now up above you see the square wave, and there is the spectrum. So let's talk about some of the things that are going on here. On the left of the FFT, you see the left scale is in dBV, that is in dB volts. Now earlier I said that you generally always reference everything on spectrum analyzers to dBm, that is dB milliwatts. But on an FFT often, because it's an oscilloscope, and remember an oscilloscope is primarily a voltage measuring instrument, it's common for it to be referenced in terms of dB volts or dB millivolts or dB microvolts. In this case, the signal that we have at the top is about 3 volts peak to peak. The analog discovery is set to 500 millivolts per division, and you see there's about 6 divisions peak to peak. And then down at the bottom is the spectrum. We'll talk a little more when we get to talking about spectrum analyzers themselves, about how this actually divides up. But fundamentally, when I was talking a little bit ago about resolution bandwidth, that is, for example, how narrow a frequency you can resolve in the FFT is called the resolution. In a spectrum analyzer, it's called the resolution bandwidth. And the reason is, I said earlier, that an FFT is actually just a mathematical transformation. It's not actually measuring the frequency. What it's actually doing is it's taking the signal that you're displaying on the oscilloscope itself, or in the case of any of the digital storage oscilloscopes, it's what's stored in memory. It's taking that signal and it is actually doing a mathematical transform. That is, it's computing frequency components from the sample points. Now what I'm going to do is switch and show you the spectrum analyzer capability in the analog discovery. Now I've got the spectrum analyzer connected. Now this isn't really a true spectrum analyzer. It's actually an FFT. It's just that it's a little better FFT than the one that we looked at earlier. I won't go into the technical specs of the analog discovery, but there are differences between the spectrum analyzer and the FFT, but they are fundamentally the same thing. So what we have here on the far left is the 500 kilohertz. The center frequency is 5 megahertz. That's right here. So this is 1 megahertz, 2, 3, 4, 5. It's a square wave. This is 500 kilohertz, which is the fundamental. And then this would be the second harmonic, but since it's a square wave, there's very little second harmonic. This is the third harmonic, which is at 1.5 megahertz, and so on. And you notice that each harmonic diminishes slightly in frequency. Once again, on the left, you have amplitude, but it's in dB volts. The analog discovery has an upper limit of 10 megahertz. And so one of the reasons that the early demonstrations here have been at 500 kilohertz or the frequencies in that area is that you can't really, if you look at this display, given that this is 1 megahertz and this is 10 over here, that's the frequency limit of the analog discovery. So this is about the most you're going to be able to see with measurements that are reliable. We're not going to be using the analog discovery as a spectrum analyzer, in large part because most of the experiments that we're going to actually be doing, particularly in the second half in part 2, are going to be RF experiments up in the cell phone bands, around 800, 900 megahertz, and some occasionally up in the 1.5 to 2 gigahertz range. So, and obviously the analog discovery isn't intended for that kind of work. But it does do a useful job of displaying the frequency information. And let me show you how you get to the spectrum analyzer on the analog discovery. Here is the waveforms screen that normally comes up. And you notice over here is the scope, and down here is the waveform generator. Over here is the logic analyzer and the logic pattern generator. You also have a voltmeter and some other things. Down here you'll notice it says more instruments. If you click on more instruments over here, a network analyzer, which is an interesting thing, we might want to look at that at some point, a voltmeter, and then down here is a spectrum analyzer. And that's where this screen comes from. And then in the upper right hand corner, you'll see is where you make most of your settings. You have to enable a track. In this case I'm using channel 2 once again because it's in blue and it's easier to see on the camera. And then up here is the frequency information, the center frequency, the span, and then the level information, and what the top is and what the floor is. And of course, like all spectrum analyzers, the floor of any spectrum analyzer is determined by the noise level. The noise level is a function of bandwidth, and we'll talk about that a little later, but it's also a function of the internal noise of the spectrum analyzer itself. So you can set the top level, but really the bottom level is one that if you try to set it down here, it's pointless because you're not going to ever be able to see anything below the noise floor of the instrument you're working with. In the last segment, I talked about the fact that the analog discovery default condition is in dB volts, whereas most spectrum analyzers default condition is dBm. And I didn't mention that the main reason for that, or if I did, I forgot to emphasize it, is that in an oscilloscope, you don't really know what input impedance that a person is going to be using. Most scopes these days have a 1 meg input impedance, and if you use a 10x probe, it multiplies that to 10 meg. So the exact resistance that you're measuring the spectrum across can vary with an oscilloscope quite a bit. So they tend to use dB volts with an oscilloscope in the FFT position. But here is how you make the conversions between those various values. You may notice that there's a chart for a 50 ohm impedance and a 75 ohm impedance. You can, of course, using Ohm's law and the power formula P equals EI, you can derive your own charts for whatever resistance you want. But these are the standard impedances, 50 being the most common, and some 75 ohm. 75 ohm is used a lot more in the cable industry and in television antennas and things of that sort. So here is the conversion. To go from one of these types of measurements to one of these types of measurements with a 50 ohm input impedance, here are the values of dB that you need to apply. So for example, to go from dBm to dBV in a 50 ohm impedance situation, you have to subtract 13 dB. So if, say, you had 13 dBm, that would mean 0 dBV. Similarly, for the 75 ohm case, you also, and notice that the factors are different. And obviously the reason is that, remember that power is E squared over R. So if you change R, you're going to change the power measurement. So in a 75 ohm impedance, you notice you only have to subtract 11.25. So this kind of chart can be useful if you're doing very many conversions from dBV to dBm, for example. So if on the analog discovery, let's suppose that you measured 3 dBV and you wanted to convert that to dBm. So over here from 3 dBV to dBm, you have to add 13. If you measured 3 here, you'd add 13, and so you'd get 16 dBm is equal to 3 dBV. Here is a chart that shows how the power ratio varies. Along the bottom, on the inner track, is measurements from 1 milliwatt, which is 0 dBm, up to 10 watts, which is plus 40 dBm. And here, of course, is 1 watt, 100 milliwatts, 10 milliwatts. Notice that for each change of 10 dB, you go an order of magnitude up in the power. On the outer track is shown how this chart would be extended. One way to think about it is if you took this corner of this chart and pasted it down here so that you had another chart over here in this corner, then it would extend the current chart. But for now, I'm going to ask you to just imagine that we're now looking from 0 dB, which is here and here, and we're going down from there. 0 dBm is 1 milliwatt, which we already know, of course, from our previous computations that 0 dBm is 1 milliwatt. Now, you may notice that this chart doesn't reference resistance in any way, and that's because in this case you're converting from power to dB power, and that is resistanceless. In other words, it doesn't matter what resistor you measure the power across. If you measure, for example, 1 microwatt, well, that's minus 30 dBm. Okay, I hope this helps understand a little of this, because it's one of the things that a lot of people coming to spectrum analysis find confusing. All of these descriptions of logarithms and dBs and power ratios and so on. And so I hope that I've clarified it a little bit. If you'd like a little more on this kind of thing, there also is a good video by Alan W2AEW on dB and dBm and so on. So once again, I can recommend his videos very highly. So let's return now to the Tektronix. And we'll go back to the channel 1 input. And you may notice I've adjusted this, as I indicated at the very beginning of this video, for quite a few cycles. Now, let me explain that I mean cycles, not samples. This isn't so much a question of how many samples your oscilloscope can take per second. It's more a question, when you're doing an FFT, of how many cycles of the waveform you have displayed, because the FFT is simply going to use this amount of information, and it is translating cycles into the frequency domain. So if you have only a few cycles displayed, the resolution is very low in the FFT domain because the number of cycles it has to work with is very small. On the other hand, if you give it quite a few cycles to work with, like that, your resolution will be better, but as you will notice, and if you watched Alan's video, he talks about this quite a bit, your total span, that is the range over which you can see frequencies, gets smaller. So at this level of cycles, when we do the FFT, you see we have the center is at 6.2 megahertz. This is a 500 kilohertz fundamental over here. So this is 1.5 kilohertz, and so on, the fifth harmonic and so on. This is a square wave. The sample rate is 25 megasamples per second. Now this is a 2 gigahertz or 2 gigasample per second oscilloscope. Why is it only sampling at 25 megasamples per second? That is because it's only the number of points on the screen in the time mode that count. And for FFT purposes, as long as you fulfill what's called the Nyquist criterion, I won't talk about, basically you have to be sampling fast enough that you're not getting aliasing. But as long as the sample rate is fast enough to collect enough samples per cycle, the only measure of how much FFT information you can get is how many cycles you have displayed, because it works out of that memory to compute the FFT. So this allows us to see the harmonics out to, let's count them, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 20, the 23rd harmonic. And the center is as shown up here. Now let's suppose we want to look at the fifth harmonic. This is the first, the fundamental. This is the third. That's the fifth. The way we do that is we use the horizontal position control over here to move the trace over until that center, that harmonic. Now remember, I pointed out this, the line at the far left is an artifact. This is the fundamental, this is the third harmonic, this is the fifth. So we'll put the fifth harmonic right in the center. And that is 2.55 megahertz. I don't have it exactly set right. It's not exactly the right value. But now we're going to zoom in by 2, by 5. And now you see, this is the third harmonic. We have the fifth harmonic centered. And this is the seventh harmonic. And now you can look in between at the other cross products. That's the way you use an FFT, but before I end this segment, I want to emphasize that an FFT is a math transformation. It's not actually sweeping the input signal with a mixer like a spectrum analyzer does. Instead, what it's doing is it's capturing a time domain waveform and then computing a mathematical function that separates that waveform into the harmonic components. I think we'll end this part at this point. I'm probably going to do 2 more parts. The next part will probably be on spectrum analyzers, and I'll show you some of those. Right over here is an Instek GSP730 and a Rigol DSA815, and I'll be using those to demonstrate the operations of spectrum analyzers. Hope to see you in the next part.